everybody. So I'm also from Professor Cook's lab in the chemistry department. We developed a methodology for tissue imaging called the desorption electrospray ionization mass spectrometry. So mass spectrometry can identify and measure molecules within a tissue by measuring a signal that relates to their mass and structure. So imaging mass spectrometry can show the distribution of molecules within a 2D tissue section or even a 3D molecule. Typical applications are cancer diagnostics, because you can monitor the differential distribution of lipids or oncometabolites that are present in normal tissue and cancerous tissue. You can also study distribution and penetration of drugs within a tissue section. You can also study developmental anatomy by looking at molecules that are expressed in different organs as they develop. For example, in animal fetuses like the pig in the picture. So we refer to it as molecular anatomy. They can give you some insights into organogenesis, cellular differentiation, and this information could be useful for biotechnologies of reproduction, such as in vitro fertilization. So desorption electrospray ionization uses charged solvent, which means that you need a high voltage and solvent to perform the experiment. And essentially the solvent is sprayed with the assistance of gas right on top of a tissue section or a tissue smear that just sits underneath the spray on a glass slide. So the analysis is extremely simple and straightforward because we can analyze tissue sections and smears with no sample preparation, that conversely like techniques like MALDI or other advanced technologies. And the way we can run an image is simply moving the spray right on top of the surface of the tissue section itself. The analysis can be morphologically friendly because we can choose solvent combinations that don't destroy the morphology of the tissue, the cellular morphology, and that means that after the experiment you can just take your tissue and stain it, or you can use it for other experiments like MALDI to get complementary chemical information. The solvent combination you're using dictates essentially the type of molecules that you can detect. One of the applications we are trying to put out there in the clinical settings is the use of DESI for tumor margin detection during neurosurgery. So gliomas are tumors that grow within the brain, and they tend to infiltrate into the surrounding tissue, essentially making tumor margins inexistent. And this poses a big challenge for the neurosurgeon to actually cut the tumor during surgery and remove as much as possible. The technology available is now really helping the surgeon to cut the tumor, especially the surgical margins. MRI images are acquired preoperatively, but once you start the surgery, the brain can shift, and so the localization that you see of the tumor in the MRI images does not precisely translate into the areas that the surgery is touching. So pathology is also done normally during surgery in order to identify the tumor type and the tumor grade, but this technology cannot be used for repeating the experiments multiple times when the surgeon is cutting and resecting the margins, because it's time-consuming and is a laborious procedure. With DESI instead, we can bring the instrument inside the OR, run analysis on tissue smears in about 2 minutes, provide a quasi-real-time feedback to the surgeon on the presence of tumor and the infiltration within the tissue.